Welcome to the second session of A2 Revision. My name is Jane Owen and I'd like to welcome you today, Stephen Jones, to talk to us about magnetic fields.
Hello everybody. So today I'm going to do a review of magnetic fields, and if we get a chance at the end I'll go through a couple of questions and give you some model answers for them. So it's 4.4. The first part of 4.4 is 4.4a, how to determine the direction of force on a current carrying conductor in a magnetic field. For that I'm going to add a little bit extra in that would be useful for you to know to go through the whole unit. So it's not necessarily to do with 4.48, but it's important to know. So first thing to recall, if you like, if you haven't already know it, is the right hand grip rule. Now the right hand grip rule tells us the direction of the B field, the magnetic field, if we got current flowing in a long straight wire. So if we got current in a long straight wire, and for example it's going upwards, all right, so I'll do I going up like that. What we do is we get our hand, we do a grip around the wire, and the thumb goes in the direction of the current, so that's obviously pointing upwards, and then our fingers show the direction of this magnetic field around that long straight conductor. Right, so in this case it would be going around in this direction here. So that's the B field direction in a long straight wire using the right hand grip rule. So that's the first one. The second one is the right hand motor rule. All right, so it's Fleming's right hand rule. All right, so I'll just call it Fleming's RHR. All right, and this tells us the direction of the force on a wire that's carrying current. Right, it's the motor rule, and if you think motor, you drive on the right hand side, so hence the right hand rule. Right, so the right hand is used, and it's because it's a motor rule there is current flowing. So is current already flowing through a conductor, and you can then work out the force on that conductor. And for that, obviously, you make right angles with your three fingers. This is our thumb, obviously, right? And that M denotes motion. The first finger has an F in it, and gives the direction of the field. The second finger has a C in it, and that tells us the direction of the current. So they're all perpendicular to each other. So the thumb is the motion, the first finger is the field, the direction of the B field. I suppose in there I should put in there the B field, and the second finger is the direction of the current. All right, so that's Fleming's right hand rule, and to go with that is Fleming's left hand rule. So this is the left hand rule. Now the nomenclature is exactly the same, right? The thumb, M for motion, second finger, or first finger I should say, first finger is B field, or direction of B field, and second finger is the current direction. Now this one is used for when current is induced, right? So there's motion, right, in a B field, and the current is induced. It's the left hand rule. So right hand rule is the motor rule. Motors tend to be turning, therefore current is already flowing. Left hand rule is current is induced by motion of that conductor. So those are three things, and it's the bottom one that comes under 4.4a. So those are things we need to know before we can move on. Right, so the next one then, B, is how to calculate magnetic field B by considering the force on a current carrying conductor in a B field, i.e. understand how to use F equals Bill sine theta. Now, what I've done here with my artistry, so please excuse my wonderful drawing, is I've got a balance scale here, a pan balance with a horseshoe magnet. So there is a horseshoe magnet. I've got a long straight conductor going through it, and this is fixed, so this doesn't actually move. I know it's not looking if it's attached, but it's actually fixed, and I've got that connected to a variable power supply. So when you put current through that, it creates a magnetic field as per the right-hand grip rule at the top there, and that interacts with this horseshoe magnet. And as we increase the current, the force increases, right? So as I increases, F increases. So that's our first statement, if you like, or the relationship. So as I increase the current going through here, the force is increasing here, and we know that because the mass scales, depending on how you set it up, will increase. All right. So that's the first one. Now, the other thing is, if I change the horseshoe magnet and put a more powerful horseshoe magnet in it, in other words, increase the B field, right? So as B increases, then also the force increases. So I can increase this force by increasing the current, or I can increase the force by making it or having it in a stronger magnetic field. The third one is, in this case, I've got a small amount of wire in this B field. If I was to increase the size of the B field, right, or have more of the wire inside the B field, also, then the F would increase. So as L, or length, increases, F increases. And this then gives this relationship. So the force is proportional to the B, the I, and the L. All right, so there's no constant proportionality. In this case, it's just literally F equals B, I, and this L. Now, the sine theta is the angle to which this wire is in relation to the horseshoe magnet. So if it's parallel to it as it is there, or perpendicular, I should say, to the B field, then sine theta usually equals, or theta equals 90 degrees, which means sine theta equals 1, and it falls off the end. And in most WJC exams or questions I've seen, sine theta has always equaled to 1. So we just remember it as F equals Bill, but don't forget that sine theta is there. As long as it's perpendicular to the magnetic field, it will fall out because sine theta equals 1. So that is F equals Bill, right? And we remember it as F equals Bill. Now, the second one is moving charges. So what I've got here is just a screen, if you like, and I've got here the B field going into my page, right? So if I just make an aside over here, just in case you didn't know, that is feathers of an arrow, if you look, going away from you. So that's into my page. And if you see it like this, it's out of the page. And it's a bit like an arrow. So if you see an arrow coming towards you, it's coming towards you. You see the flight, it's going away from you. And that's the same we use for the B field. So I've just done a screen and I've just added this B field, which is going into my page. Now, if I take a positive charge, whatever that positive charge, so let's just take this positive charge here. There we go. Make it positive. Now, when it goes into this direction here, we've got a positive charge moving. As soon as it goes in here, it's going to experience a force. All right, and in this case, the force is due to Fleming's left-hand rule. All right, so if you follow the left-hand rule, you get your left hand out and you have your first finger, the field, going into my page. The second finger, which is current. Now, current by this standard is a positive charge, so it's going from left to right as I'm looking at it. Then the force, according to my thumb, is upwards. All right, and it will bend upwards like so. All right, so in this case, let me just put up in here, I is in this direction. All right, now then, if we put a negative charge in here, oh, let's go back to my blue pen. If we put a negative charge in here, all right, there it is, and we put it in, well, let's do it up here rather, and we send it in the same direction, then Fleming's rule still applies. Well, lots of students think that, hang on, it's moving this way, so it's going to bend up again. However, by definition, right, it's a negative charge, so negative charge is flowing in the opposite direction. So what we have here is a current going in this direction by definition, which means that this charge will move in this direction. Okay. Now, again, the greater the B field, right, the greater the deflection, right? So, or the smaller the radius, right? So the greater the deflection. Space here, guys. All right, so that's one thing, right? Now, if you put a bigger charge on there, it can experience a bigger force. So the greater the charge, all right, again, the greater the deflection. All right, and also the greater the velocity. So as it goes in a lot faster or moves into this field faster, it's also going to experience a greater deflection. So the greater the velocity, the greater the deflection. And that's where the equation comes from. So what we've got here is F equals BQV, where B is the B field, Q is the charge, and V is the velocity. And again, in this case, we have sine 30, which is the movement of this, or the angle of this in relation to the magnetic field. So if it's perpendicular, sine theta will be sine 90, which all with, so sine 90, as we know now, will equals 1 and falls out. Now you can also know this as F equals BEV, right? Because BEV is easier to say than BQV, doesn't matter. But if we say F equals BEV, we're usually relating it to the charge of an electron, where BQV is the charge, whether it be a proton, electron, or whatever, right? So you can know it as F equals BQV or F equals BEV. Now, most students remember it as BEV because we got Bill and BEV. So we've got F equals Bill and F equals BEV. Just remember, if we use an E, we usually saying it's about an electron, not necessarily about a charge or a positive charge. Right, so then D, the Hall probe. So it's applying a little bit of what we've just learned already. All right, so what I'm going to do now is going to do some drawing. So you'll have to excuse my drawing in this one. It's a bit challenging to draw. Right, so I'm going to just draw a semiconductor slice, if you like. I'm going to try and draw it as neatly as I can. That's not too bad. There we go. There. So that's the semiconductor slice. I'm going to put in it a bit, or I'm going to put a B field. Let's change my color and put a B field through it in this direction here. All right, so I'm going to go like that. I'm going to call that the B field. So we got a semiconductor slice. It has a thickness T, and it has a width across there, W. All right, so there's a width there and a thickness there. Now, let's put in here a positive charge. I'm going to use a positive charge, and I'll go through it if there's a negative charge later. So I'm going to put in here a positive charge, and we're going to have current flowing up, not very up, all right, through here like this. So this is I. That's a definitely rubbish current flow through that wire, isn't it? So the current is flowing through here, and I've got this positive charge here. So if it's in a B field, the first thing to realize, all right, so point one, if you like, is there's a force due to this B field, all right? And you can work out the direction of that force due to the left-hand rule, all right? So because it's a positive charge, then, and I'm talking here a positive charge, current is flowing upwards, this positive charge is flowing upwards, then all these forces, if you think about it, or all these charges due to the left-hand rule, all end up, let's change the color of my pen again, on this side here. So these positive charge, let's make a positive charge there in green so we can see a bit clearly, all end up on this side here. All right. And if you've got a positive charge build up on here, then obviously any negative electrons on here will be forced over to this side. So this becomes negative. All right. So point two then on my little chart here is positive charges move to left-hand side. Well, if they are positive charges as in protons, however, if we're talking about positive charges, and here I'll talk about later, then only electrons move, you know that, but these would be positive charges as a flow, right? Or if you know your physics, there'll be holes. Move to the left-hand side, and negative charges move to the right. All right. And because of that, we then get something called a hole voltage. So if I put my meter between there and there and connect it up, because I've got a potential difference between one side and the other side, I've got a voltage, and we call that the hole voltage. So we have VH, or subscript H, i.e. the hole voltage, between the sides. All right. And that's due to the charge buildup. There we go. So that's that. All right. Now, eventually, all right, don't forget that these charges have experienced a force to move to the left. But as that becomes more positive, these charges will experience a repelling force from that. All right. So we've got this force due to the B field to force them to the left. But then this becomes more positive this side. So you also have then this FE, this force due to electric field, will build up. So eventually this FE will equal FB, and charges move through undeflected. Okay, and that will be when the maximum hole voltage is achieved. So let me just make some space here a second. Let me just go up to here. Where is my, let's find the mouse. Let me make some space in here so I can get a little bit more in. There we go. Right, let's go back to my pen. Now, toolbox equations for this. So there, we do need a couple of toolbox equations. I'm not going to go into the derivation from first principles because it's not required anymore. It was required in a few syllabi ago. So that's where we are. But there's a few things that you really need to understand. So we know that FB is equal to Bill or Bev. Right, in this case, because it's a moving charge, it's F equals Bev. I'm going to say BQV for this, all right, but because I've used a positive charge and rather than electron. And you may be aware that F equals EQ, right? That's the force due to the electric field and the charge, right? And I'll just put an aside here that E equals this hole voltage over the distance between the two. So the E field between this side and this side is W. So in this case, it's W rather than D, and the VH. So it's VH over W in this case. All right. Now, if you notice, right, if I equate the two of them, I've lost my pen. There we go. So BQV equals EQ. We can cancel them out, and we've got BV equals E. All right. So you can solve that, but what I'm trying to get to is says that VH is equivalent to the B field. Well, we haven't got that yet, so what I've got to do is put VH over D in. So if I take this over here, is BV is equal to VH over D. Now D for this is a constant, velocity for this will be a constant. So what I've got is B is proportional to VH. All right, as long as the velocity remains constant, i.e. the current's constant, all right, and the thickness of this doesn't change, which it won't do. So understand that VH is proportional to B for constant I. We just have done it. All right, so B is proportional to VH when V and D are constants, and V can only be constant if I is constant. Moving on. All right, so the shapes of magnetic fields due to a current on a long straight wire and a long solenoid. Let's look at the long straight wire first. Where's my mouse gone? Where am I writing? There we go, I'm down there. Right, so let's do a long straight wire. We've sort of attempted this at the start of this session. So I have a long straight wire, and then the shapes are concentric circles around this wire. All right, so the concentric circles, i.e. one inside the other, inside the other, inside the other, inside the other. like so. And again, we can work out the direction of these by knowing where the current is. So if I say the current, like I did at the top, is in this direction, then these go around in this direction here. All right. So these are what's the plot? There we go. Concentric circles. All right. So those are concentric circles. And just to clarify, right-hand grip rule gives direction. Now, secondly, then, it's in a coil. So if I draw a coil, this will be entertaining. Ah, it's not so bad. Right, what's it look like in here then? I'll change my colour of my pen for this. So what we've got is exactly the same as a bar magnet. It goes out and back in, and the same here, out and back in. And if you're drawing these, always make sure you do at least 2 field lines, right? Make sure they don't touch, make sure they don't cross. Right, exactly the same rules as you learned in Key Stage 3 for bar magnets. Oh, it's not so bad. All right. Now the direction of this can be again found from the direction of the right-hand grip rule. This time we're going to use it slightly differently. What I've done here is a little thing, hand here, and if we say that as the B field, all right, so we use our thumb to say the direction of the B field. Now the fingers tell us the direction of the current, right? In this case, you can see I'm looping over. So if we relate this to this diagram here, if I say the current is going up this one, across the top, 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 and down through that one, then I've annotated it the same as this, if you like. I'm coming across the top of my wire, so that's my current there, I, and then the B field will be going this way out of the center of the coil, which means that my direction of my arrows goes like that. All right, so it comes out of that and into that. So this would in fact be a north, and that in essential would be a south. All right, and that can be found from the right-hand grip rule again. Right, now the equations that relate to those. Again, if I just draw a straight wire, or attempt to draw a straight wire, let's look, see if I can get it done. There you go. Oh, it's still in green. Who cares? Right, if I draw a straight wire, and we know that my field goes around it like that, right, then the equation B equals, it's there, look, mu naught Ni. Right, now, sorry, wrong one. That's just wrong one. B equals mu naught I over 2 pi A. So mu naught is a constant. All right, so mu naught is a constant, and it's a value. It's 4 pi times 10 to the minus 7 henries per meter. All right, when you're putting this into a calculator, be aware that a lot of calculators don't like you putting in 4 pi and then putting times 10 to the minus 7 after it. They tend to prefer you to put it as pi times 4 times 10 to the minus 7. So I'd suggest if you have a practice of putting that into a calculator to find out what the value is 4 pi times 10 to the minus 7 is. So a lot of calculators don't like it. If you've got a fandangled one, a modern one, it might like it, but I know none of mine do. So just be aware of that. I is the current, as you'd expect I to be, and then A is the distance from the wire to the point that you're taking, right? So that would be A. Consider it a bit like radius, but it's not a radius, is it? It's a distance from the wire, right? And that's why it's got the nomenclature A rather than R, which you think, well, that's the radius out. Yes, it is the radius out, but it's a point, a distance away from the wire, therefore it's A. All right, so A, point, or the measurement or the distance from the wire. Okay, so that's the first one. Let me get me more space because I just realised I've run out of space. So let's just get into type. Let's go back to, I'll go to blue for this one. Now for a long coil of wire, and you see my wonderful drawing skills again. right, for our coil, there we go, that's all right. It's slightly different. We've got B equals mu naught Ni. Now, mu naught and I are the same as up here, right? So there's no change there. So N is the number of coils, or the number of turns. All right, so that's all it is. All right, so it's exactly the same. So mu naught and I is same as what we've used up there. Now, if you take that a bit further, oh, hang on, I need to move that. It's got in the way. That one I want to move. Yeah, there we go. If we take that a bit further, let's just get back up a little bit. There we go. If we take a bit further and put something like an iron core in that, right, then the magnetic field strength or the magnetic field increases by a factor, right? So if I was to put this iron core in, right, so this here increases B by a factor mu R. All right. So in this case, it's the same equation, if you like. All right. So we got B. If I call it B, and if I call that B naught, then I can say B equals mu naught mu R Ni. All right. Or in shorthand, you can say B equals B naught mu R. Right, so all this iron core does is increase the B field by the factor mu R, which is specific to the material or the item you've put in there. All right, so something like iron, mu R will be quite a large number. Okay, now it gets a little bit tricky, this one. You have to get your head around this one to fully appreciate what is happening. So you might have seen this in school with a current balance. Essentially what we've got is a long straight rod, or two long straight rods in this one, with current going through them, in this case in the both directions, in the same direction, sorry. So the idea of current conductors exert a force on each other and predict the direction of these forces. So what we're going to do is, if we look at I2 for starters, right? If we look at I2 and say, hang on, let's use the right-hand grip rule with that. What we've got is the field line, or the B field going around it. So let's draw a B field going around it. See if I can do this. There we go. Oh, I've gone through it. Doesn't matter. So B field going around it. And if I go bigger and bigger, then eventually I'm going to go through wire 1. Right. So you can see here the B field in here is interacting with I1. And in this case, as it's coming from the back to the front, the B field is coming through in this direction. So let's just change the color of that. So the B field is coming through in this direction here. All right. Okay, so the B field induced or created, if you like, in I2 is going through I1. Now, if a current in a wire is in a B field, we know that that is going to produce a force or induce a force. So that force then, if you think about it, is the left-hand rule. All right. So let me just make a note of where we are to start off with, so you can just follow me. So number one then, current in I2, right, induces a B field. All right. And that is the right-hand grip rule. All right, and then 2, the B field cuts through wire 1, right, and point 3 induces a force due to left-hand rule. All right. Remember, the left-hand rule is the generator rule. Right, so we're inducing a force. Right. Now, so what is this force experienced on wire 2. Well, if you think about it, the force on wire 2 is equal to, oh sorry, force on wire 1, my apologies, just to clarify that. Force on wire 1 is due to the B field in 2, all right, the current in 1, and the length of the wire that they interact with each other. All right, so the force on 1 is equal to the B field in 2, the current in 1, and the length of the wire. Similarly, we can say the force on 2 is equal to the B field in 1, the current in 2, and the length of wire. Now, if we look at this, then in this direction, if you use the left-hand rule, right, and follow it through, then the motion for this one is down, all right, because we've got the B field coming out, the current going that way, the motion is that down. Now, if we reverse our explanation here and do the opposite, all right, and do the right-hand grip rule on the top one and see what the force on the bottom one, right, it moves upwards. So this would move upwards as well. So essentially what we've got is if currents are in the same direction, they move towards each other. And I need a bit more space there, don't I, guys? Let's go up there and give myself a little bit more space. Oh, didn't go into there. There we go. Enough. Let's go back to there. And if currents are in opposite direction, I think you can work it out if you haven't already. If you have realized, they move away from each other. All right. So if the current's in the same direction, they're going to be attractive. You can work that using the right-hand grip rule and the left-hand rule, Fleming's left-hand rule. And if they're in opposite direction, they will move away. And don't forget to use the right-hand grip rule for that and the left-hand rule. Okay, so those are two rules you'll need to work out in which direction they both move. Now then, quantitatively, how ion beams or charged particles deflect in uniform electric fields and magnetic fields. So I'm going to go back to something I drew at the very start, right, which is this area which experiences or charge experience a field. But before I do that, let's just go for uniform electric field. So let's do two plates. There we go. There's one plate. There's another plate. Let's put a potential across them. Let's say that's positive, and let's say that's negative. All right. And let's take an electron. So there you go. It's an electron, and let's accelerate it through this. We've already seen from above. Oh, actually, no, we haven't. We know electron is negatively charged. It's a positive charge plate. We know that this is going to be accelerated towards a positive plate. All right, so we know that. If we put an alpha particle in, which is positively charged, for example, and we accelerate through there, we know it's going to be repelled from the positive and attracted to the negative plate. Now, electrons are a bit lighter than a helium nuclei or whatever, positive charge, so therefore it's going to bend a little bit quicker. All right, so it's going to have a tighter curve than that positive charge there. All right, so that's what would happen in an electric field. Let's do the same thing now. Let's put it in an electric field, actually put a B field in there as well. So let's do a positive charge as we've just done. Let's do a negative charge down here. And let's put that in a field. Again, let's have this field going into my page. All right, so all this is in my page. Now, if I do the same thing and take an electron, right, and whiz it through that way, we know it's going to be attracted to that positive charge. But due to the right-hand rule, all right, so due to the right-hand rule, left-hand rule, all right, so due to the left-hand rule, we know that this is going to experience a force. Now remember, it's an electron, so actually, all right, I just changed my color, because it's an electron, a current is actually flowing in the opposite direction. So even though the electron's moving that way, it's going to want to deflect it there. Because it's in this field, it's going to want to deflect the other way. Now, because it's F equals BQV, the force is proportional to the velocity. All right. So therefore, if it goes through and it continues to bend upwards like this, then really what we're saying is it's going through too slow. If we put it through and it bends this way, then the B field is the bigger force, right? So, and therefore it's going through too fast. If we can get it to go through like this, straight like that, then we know that the force due to the E field is equal to the force due to the B field, right? And it's going right at the right speed. So what we say here is that FE equals FB. And if we look at that, then what we're saying is EQ equals, well, FB is BQV. Q's are the same. So what we've got then for this one is the E field is equal to BV, right? And you could use that in equation to solve for a value of E, B, or actually V. So E over B would give you V, right? Where V is obviously the velocity. All right, and we call that a velocity selector, right? So that is a velocity selector where electrons would only go through a little slot over here if they're going at the right speed, and we can change the speed, or we can control that by having the size of B field and the size of E field. All right, so only those that go through at the right velocity would go through at a straight line. All right, let's move down a little bit further. Now then, so applying this then to accelerators. The first one we're going to look at is the LINAC, and that just stands for linear accelerator. Now, there's a few things to notice about the linear accelerator. These are called drift tubes, and these drift tubes aren't the same length. They get longer and longer and longer. All right, so the first thing to notice about a LINAC is the drift tubes get longer. All right. Now, and that is to make sure that because these particles, these protons, if you like, that are leaving here, they get accelerated between the drift tubes. So acceleration happens here. So between the tubes, because inside the tube, there is no net force. So they're only accelerated between the positive tube and the negative next tube. So if this was a proton, it'd actually be repelled now. So the proton will probably be a little bit here at this moment in time and be pushed from this tube and pulled into that tube, and it accelerates. Now, as it accelerates, it's going to gain kinetic energy, K equals half mv squared. In other words, the velocity is going to increase. So the drift tubes get longer because the time spent in each drift tube must be the same. All right, so the time in each drift tube is constant, and hence they get longer and longer. All right, so drift tubes get longer because they have to spend the same time in each tube, right? Because they accelerated between the tubes. Now then, because of that, the frequency is fixed. So it's a fixed frequency system. So once you've built it, you've got your drift tubes, you've set it up, you've got a fixed frequency there, and therefore that's it. So your maximum energy is dependent on the length. And therefore these LINACs tend to be quite long. All right. So they tend to be quite long to get the energies required to accelerate them. Now that's the first thing that's the first ever accelerator we had. So we had a Linux, and we found that we could accelerate them using this method. So key points.
Steve Jones, I think we will have to finish here because it's 6 o'clock and people have other revision sessions to go on to. So my recommendation is to add a few notes to what is left.
Thank you very much for pointing that out. You're quite right. What I'll do for you guys is I will add notes to this and highlight this before I upload it. There is two to do. There's the cyclotron and the synchrotron. Cyclotron's underneath the synchrotron at the moment. I'll upload that and I will share that with e-sgol for you to do. Thank you very much.
Okay, well, can we say thank you very much, Steve Jones, for your presentation on magnetic fields. That's quite a lot to cover in just 40 minutes. And to stop short, you know, just of a couple of things, I think is you've done yourself proud. And please join us again next week and the week after. And we'll have practical skills next week and electromagnetic induction the week after. We look forward to seeing you and answering your questions. And goodbye for now.